we're going to take a slight little pivot and actually focus on a very specific farm and a case study that we at Duke University have been working on for about 5 years now. I'm Jason Elliott. I work at the Duke Carbon Offsets Initiative, and my co-presenter, Marc Deshusses, is our faculty at the Pratt School of Engineering at Duke University, as well as our, at least my favorite expert in anaerobic digestion. To kind of set the scene a little bit, we're going to be talking about renewable energy certificates, carbon offsets, and generally how the system functions. Starting with just a general small introduction, and then Marc's going to take a deep dive into the project, how it functions, and is it successful? And then I'm going to take it over again and start talking more about carbon offsets, talking about renewable energy certificates or credits, and then we'll hopefully have some time for question and answers, which actually might feed right next into the open discussion period. So looking at Loy Ray Farms, we are about an 8,600 head feeder to finish operation, meaning we are kind of the babysitter of the hogs when they first are young. We feed them until they're ready to go, and then they're picked back up and taken to slaughter. All the waste through their entire lifespan is set and stays on the farm. Our farm is unique compared to what a lot of other farms we've been talking about, since we are west of where we currently are, about 2 hours, versus most of the hog farms in North Carolina, as we've seen from many of the maps, are concentrated in the eastern portion. This is one of the first swine waste to energy projects that has happened in North Carolina that has also paired it with a denitrification basin. And Marc will talk much more about that because that's way out of my wheelhouse. But the system, the purpose of it is to capture the methane from the waste and channel it through a bunch of tubes and pipes and creates a gas that we use and burn on-site for energy. Or if we have enough, we can actually flare it. Both of those processes create carbon offsets. Only using the microturbine creates a renewable energy certificate. We have actually been really fortunate to have a large number of partners for this project, and so some of the most important were Google and Duke Energy in terms of the partnership. Duke Energy would get the renewable energy certificates as well as helping out with part of the funding, and then Google would get some of the carbon offsets as well as Duke University, and they helped out with a lot of the funding. And then we also have a couple grants that came from the USDA as well as the NC Division of Soil and Water, and then our on-the-field at the farm crew at Kavanaugh Engineering Solutions has been instrumental and most helpful in terms of daily monitoring and making sure that the system is running, and if it breaks, which it happens a lot, it gets fixed fairly quickly. So I'm going to pass this over to Marc to talk a little bit more about the system design.
Thank you. Yeah, I'll give an overview. I'm going to try and avoid too many numbers and too many details, but try and get you a sense of how the waste flows from the barns to the treatment system, and then how we are able to make energy. So you see some pictures here. Again, we have about 8,600 hogs in 9 barns, and they get there when they're little and cute, and then they leave when they are really, really big. Traditionally, the waste has been flowing into the lagoon, and the new system, as was mentioned, comprised of an anaerobic digester, which is about 2 million gallons. Anaerobic digestion is a natural process. It's very robust. It is a complicated process, but it occurs naturally. We don't need to get into the details of it. I think it's just important to understand that organic waste is converted into methane, and methane is the same gas that you have in your cook stove, and carbon dioxide. So about 60% methane in biogas, and you can burn it and recover energy. You can burn it and make electricity, and that's what we do at the farm. I should mention, and probably most of you know, is that methane is also a very potent greenhouse gas, 25 times more potent than CO2, and it would naturally be emitted from the lagoon. So as we are producing energy, we're also making something which is good towards limiting the emissions of greenhouse gases. So very quickly, again, you see some pictures here. of the system, and let me walk you through how it works. We have 9 barns here. The pigs are on slats, and then each day the farmer pulls the plug on 2 of the farms, and the waste flows by gravity into the anaerobic digester. He does that Monday through Thursday. Friday, only 1 barn gets flushed, and there's no flushing of the toilet at the farm on weekends. It's about 70,000 gallons per flush. Again, there's roughly about 1,000 pigs in each one of the barn. As an aside, it's interesting, a pig produces about 3 or 4 times as much waste as a human. So you can look at this as a small city of, I don't know, something like 25,000 people or 30,000 people, depending, of course, on the size, but I'm like oversimplifying here. So here in the digester, and you can see a picture here, which is in-ground, relatively simple construction digester. The gas is produced and is captured underneath this cover. There's a lot of engineering that went into that, but the system was designed and built in a way that is relatively simple. The gas goes to a microturbine, which produces roughly 65 kilowatts of electricity. Jason mentioned earlier that there is a flare as well. Personally, I don't like to burn gas because in a flare because it just makes it flame, and you don't get much recovery of it. But at least you avoid the emissions of methane. So whenever we can, we try and produce energy into the microturbine. Let's follow the waste. Whenever there's a flush, it goes into the digester, and then some overflows into this aeration basin, which isn't shown on this picture, but you'll see it on subsequent pictures. And this is an open basin that we actively aerate. It is designed to take care of some of the nitrogen. It's intermittently aerated, which means that for some time during the day, there's air injected into it. And then, again, that takes care of the nitrogen and some of the residual organics. And then there's a quiescent zone from which water is being pumped to replenish the pits. So that's the general idea. That's about 1 million gallon in volumes. And I think that's the gist of it. You can see here some pictures. Again, here's the digester inflated with gas. This is some of the equipment. This is the microturbine. It's really just a jet engine run on biogas. You can do it also on just an internal combustion engine. And here's some pictures. That's the aeration basin. Some of our researchers measuring air emissions from the barn. This is me measuring odor. We have different ways that we can measure odor and do some impact assessments. And you can see here some of the characteristics of the systems. I'm not going to read through all of these, but just want to point out that Duke decided not to, Duke and Kavanaugh together, not to take any patents, so it's an open source. The idea is that as we go through it and improve it, we make it available and hopefully see more of these systems being installed. It significantly reduces greenhouse gas emissions as well as odors. We had an event with the neighbors shortly after the system was installed, and the informal feedback was that they had far less odor in the neighborhood. And you can see some numbers here, as was mentioned earlier. There's more biogas produced in the summer because the system is warmer, and of course then more energy produced, but this is also when the farm needs more energy to run their fans. It turns out that at this system there, there's no electricity re-injected into the grid. It is built in, but for various reasons, it is not happening. And so my group, we do a lot of waste treatment studies and research, and one of the things that we did was to understand the material balances through the system. I know there are too many numbers here, but I think the idea here for you to remember is that we try to really understand how the waste circles in the system to then being able to get to some numbers that Mike Williams was showing earlier in terms of percentage reduction and so on. Here you can see that at different points in the system, we're just quantifying how much material flows through on a weekly basis. And this enormous amount of waste, again, because there's so many animals concentrated in one very dense location. And so just one more graph here to show you how much we removed. Those are waste that we can actually track the disappearance and we can account for. COD stands for chemical oxygen demand and BOD for biological oxygen demand. It's a measure of the organics. And we can see that in the digester, we've got a massive amount that is removed, and of course that's converted to biogas. So we are able to recover the resources with that. It's on a different graph here because the scale is different. You can see how much is being removed in the aeration basin. The aeration basin here, that's the primary purpose of it. The anaerobic digester is not designed to control nitrogen. And phosphorus, of course, is important. You can see that the percentages here corresponding to the removal, and those numbers are very good. And so I think one of the take-home messages is that with technology, as Mike Williams was saying, we can provide solutions, and we can iterate, and we can perfect them. But of course, there's a cost associated to that, and Jason is going to get to the cost, but there's also other benefits as well. So I'm going to turn back to you.
Thank you. I hit B. So I'm going to start with a general question of the audience. Who here knows what a carbon offset is? Good, more than our students normally do, which is great. But I'm going to go ahead and seeing as there's some individuals who don't quite know, I'm going to flex my presentation just slightly while the slides will not reflect everything I'm saying. Hopefully it'll at least stick. So carbon offsets generally, it's a reduction or removal of 1 metric ton of carbon dioxide equivalent that is used to counterbalance or compensate, offset, emissions from other activities. The reason why Duke University is interested in this is that 2024 is our climate neutrality year, where we are trying to reduce all emissions on campus to 0. Obviously, just by the very nature of doing any activity, flying, commuting, using energy, we're going to have excess emissions that we're not going to be able to reduce by doing on-campus tweaks or fixes or efficiencies. And so my office is responsible for identifying how do we meet the goal of meeting, I think we're estimating 185,000 metric tons that we'll need to offset in 2024. And so our program was developed, and actually Loy Ray Farms was our very first project that we've ever done. It's our flagship, and we still are running it. I think we've got it slated for the next 6 or 7 years that we're going to be working on it. But a carbon offset can look like a large variety of things. Wetland restoration can look like energy efficiency, urban forestry, waste to energy, and renewable energy. And so for each of these aspects or each of these types of projects, there's certain rules that they have to follow. Swine waste to energy has a lot more than some others, mainly because we have also health regulations and waste management regulations that we have to deal with to make sure that whatever project that we're doing doesn't disrupt any of that flow. And so I'm going to talk briefly about this concept of PAVER, P-A-V-E-R, and that's the kind of general idea of what a carbon offset needs to meet, the criteria that it needs to meet to become an offset. And so P, permanent. So the emission reductions that we create from a project have to be permanent in nature. And so if we think about waste to energy, you burn that gas, the methane, and turn it into carbon dioxide, it's not going to turn back into methane. At least that's not my understanding of how that works. And then we're going to talk about additionality, the A part of PAVER, and this one is kind of the really sticky issue in a lot of cases, because you have to think about the counterfactual. What would have happened in the future versus what you are actually doing now to influence the future. And so we can look at this type of project, Loyd Ray Farms, and be fairly certain that the farmer would not have been able to do this kind of project on their own It's very costly, which we'll get into at the end. And so we knew that just based on our goals for this project, that we wouldn't necessarily within the next 10 years be making the world different or the same as what it would have been if we did not act. The next one, V, verified. And so each project that we do, we have to make sure that it's verified in some way. They have to check our math. We have to make sure that we're meeting all the general requirements that are put under certain verification bodies. And so very timely for this, we're actually undergoing verification for Loy Ray Farms right now. This is a process that the Climate Action Reserve, which is mainly based in California in terms of their carbon markets, they have rules and regulations about what a verifier needs to check upon to make sure that we're doing everything properly. And so we have to do a site visit, which will be coming up soon. They look over all of our math, all of their databases that we have, as well as looking and talking with people like Mark, our Kavanaugh associates, and seeing, are we doing what we're supposed to be doing and doing the math properly? The next letter, E, is enforceable. And so we have to be very sure that the offsets that we're getting can't be claimed by anybody else. And so in order to not have this double counting issue that you can see in other markets as well as a potential issue, we have tons of contracts. Contracts that are way above my head, and that's why we have a whole department at Duke University that deals with them. And then the last section is R, and that is to be real. And so there's some instances in the past about carbon offsets where you can go to the site where they say they're going to be, and they actually have never existed. Or the math is kind of flawed, so it might overestimate how many offsets are actually being generated. And so we have to work and make sure that they do a site visit to make sure that Loy Ray Farms is there. It is, trust me. And then make sure that all the math is pointing to the exact same numbers that they would have gotten using their formulas. To kind of like take a deeper dive in a little bit, so pretend this is Loy Ray Farms. This is a very simplified version, but on the far side, there's going to have the traditional style where all the waste emissions are just going into the atmosphere. And then an organization comes in and says, hey, I think we can build an anaerobic digester. And so we came in, developed a system that doesn't look like that. Instead, it's a covered plastic-based lagoon. And then we can take all of those emissions that we are siphoning away and turning into biogas and burning or using in the microturbine. And then we get carbon offset credits. As Mark mentioned earlier, methane is a more potent greenhouse gas than carbon dioxide. The science is not quite fully accurate. Some people say 21, some are up at 35, some are going up to 50. And so we use a very conservative number because our goal at Duke University is not to overestimate our impact. And so we use 21 as our number since that's what it was when we first started. So kind of looking at how the farm generates offsets, this is a photo that Mark shared earlier. This is our microturbine. Inside it is the mechanics that it'll burn the gas and create energy. The energy that we create is sent back to the grid, and the carbon offsets we just calculate ourselves and keep within a database because it's hard to grab them. And so that plus the flare, which we use very sparingly. We only use it on the chance that there is an overabundance amount of gas being produced, particularly when it's 100 degrees out in the summertime. And it's been really great that when this is turned on, it actually works very quickly and very effectively, so we don't actually have to run it that often. This is the only time I've ever actually seen it on, and I thought it was really cool. And it reminds me a lot of the flare systems that you'd normally see at more landfill-based projects. But those things equal offsets. This is a fairly small project in terms of offset projects in the entire nation. We only have about 2,000 to 3,000 offsets per year, but those offsets are split between us, Duke University, and Google. Now we're going to segue into the other part of my presentation, the renewable energy credit or certificate. This represents the property rights to the environmental, social, and non-power qualities of renewable energy generation. And so if you can think about renewable energy coming from a solar panel, some of that is purely electrons, and that's just the energy aspect. The other is everything else associated with it, the co-benefits, the renewable aspects. And so we can decouple those things the energy goes to the grid, and Duke Energy will take the renewable energy credits and use it towards their renewable energy portfolio standard requirements. By 2019 or 2020, they are required to have 0.2% of all of their energy coming from swine waste. We're not quite there yet. There's a lot of movement actually happening in Duplin County, which we've talked about a lot today, but they're trying to figure out how can we centralize some systems, because we have this one by itself and it's a very expensive project, but if we can centralize it and maybe have a larger digester in the center of 5 or 6 adjacent farms, maybe you can have economies of scale, lower the cost of that, and maybe get to a place where it's a little bit closer to traditional lagoon style, or at least $125 per 1,000 SSLW, steady state live weight. Yeah. So with renewable energy, it's only when the microturbine functions. And so we push as much gas as we can to the microturbine because we can get offsets and renewable energy certificates. And then that creates about 300 to 400 RECs per year, which is about 300 to 400 megawatt hours of energy, renewable energy annually, which goes to Duke Energy. This is something that they're now helping develop a lot of other projects because they're trying to meet this goal. This is such a, like, 0.00001% of their energy needs, and so they've got a lot of work to do. And this last little bit, since there was a little bit of talk about costs, we took all of our capital costs, and the system has been rebuilt pretty much one time over. And so we have the microturbine, we have the conditioning skid, which removes a lot of the moisture from the biogas so it doesn't corrode certain processes in the microturbine. We have the digester as well as the aeration basin and all the pumps and things like that that are associated. All of that added up is about $1.5 million. We're getting ready to replace the cover, which is another maybe $150,000. So this thing keeps kind of going up. Annual operation and maintenance, a lot of that is, sometimes it might take electricity for the system to run. We pay Kavanaugh Associates to make sure that the system runs. And so it's all of those things added up. And then there's some small revenues that we can get from the offsets and the renewable energy credits. Ideally, this would be a thing that could help kind of tip the scale back a little bit to make it potentially more financially feasible for farmers one day. But obviously, $42,000 doesn't quite meet the needs of 1.5 million. And so hopefully we can figure out how that works out a little bit better in the future. But we're sitting at around $210, and we're hoping that if we were to redo this entirely, that we would pick different methodologies and different mechanisms and companies to work with that would help kind of ameliorate some of that cost and make it closer to 150. But yeah, I think now is questions, unless we want to go ahead and roll it into the open question discussion time.
Mike, I'd like to invite you to come back up here and open it up to the audience for questions.
I'm sorry, did you say you don't have an interconnection where you put it back up to the grid? Yeah, so the question is, why are we not pushing energy back to the grid? And it has to do with who's the provider there, and then how much does the farmer pay for electricity, and how much he would sell for. So I could make a very long answer, but that's kind of the context. As Jason said, there's been some upgrades that were done, and now we have the capability. The reality is that a lot of the energy that is produced is reused on the farm for either running the system or for the fans and other stuff, and a little extra is I mean, it's a small amount. Quick follow-up. Your comment about the REC determination, did I understand you said that you do consider externality? Economic externality?
Could you kind of clarify that a little bit farther?
Societal.
So the renewable energy certificate is all of those positive externalities and that are associated with renewable energy generation, not the actual electron of it. And so we can use the energy on site, but that renewable energy certificate and all of its renewable wonder goes to Duke Energy.
And I want to give the engineer answer to the REC and what I understand it. And so, these actually are true dollars. People are paying for it, and there's a lot of confidentiality around the cost of a REC, and in particular a swine REC. And so what I hear from rumors is that the swine REC is worth a lot more than another REC. But we haven't been able to hear a real number. But so apparently it's worth a lot. So maybe the numbers that Jason was showing, would be better. I think I truly agree with you that if this market was more vigorous, the numbers could swing. I also think it's quite fascinating to think that farmers have been growing, crop and raising cattle and pigs for thousands of years, and now they can get into a new business model. They can be starting to sell RECs and carbon offsets, which is, diversification.
So this question is for you, Dr. Williams. You mentioned that consumer advocacy programs have been very effective in reducing the use of antibiotics in animal feed. And I was wondering if you could give us some ideas as to what type of consumer programs or the structure of a consumer program that would be very effective in pushing for the, decommissioning of traditional lagoon and spray field systems, or pushing for the adoption of super soils, Terra Blue, the types of anaerobic digesters we see on Loy Ray Farms. Would such a consumer program be effective at spurring the type of technology change that we're looking for with animal waste management?
The reality, putting it in the concept of the antibiotics, is that the retailers are making the demand based on input that they're getting from their customers. So I think any type of change has to be from the consumer perspective. That is where I have seen more traction, more so really than policy, or more so than environmental regulation policy. So it has to be consumer-driven relative to the market value.
So would that take the form of some sort of label on a meat product saying this pork or this ham was grown on a farm using this?
That's what we're seeing related to antibiotics.
And I guess my final question is, if cost were not an issue, what is the best type of technology in terms of scalability, wide scale adoption at the 2,000 plus CAFOs in North Carolina and across the country? What type of alternative waste management approach would be most effective in terms of reducing pathogens, reducing emissions, odor, things like that?
That's a really, really good question. And I'm going to answer that question based on input that I get from the producers. And I'm going to be very candid. I've heard a lot in the last 2 decades from producers that, I don't mind a new technology on my farm, but I want to grow hogs. I don't want to be having to deal with bells and whistles that are going to take up my entire day in an area that I may not have any expertise. And I'll be real honest. The Julian Barham farm, and this is not intended to be a negative comment towards our producer community in any way, but Julian Barham has an engineering degree from NC State University. He likes doing the stuff that he does with his digesters, with the nitrifying tanks, with his greenhouses. So my answer to your question is, I think it's going to have to be a co-op type model or some type of model where there would be a turnkey group that would handle all of the operations for the producers that would choose that. And that has to be part of the economic component as well.
Okay, thank you.
Hi, this is a question, I think, for Mike. Kind of a big picture question. I appreciate the tremendous amount of work that's obviously gone on for the last 15 or 16 years to try to develop these solutions and some of the constraints to adoption. I work with a lot of small-scale farmers also in eastern North Carolina who are raising hogs very differently. I mean, it's a much smaller scale. They're outdoors on pasture. They're in the woods. And they're trying to address consumer interest and growth and demand for not only just some of the environmental issues and the antibiotics, but also humane treatment of animals, workers, et cetera. So they're trying to develop a system that, from a multifaceted perspective, is addressing a lot of the consumer concerns. And one of the things that's frustrating for me is that they're not going to benefit from any of the research and technologies that are being developed to address the CAFO model of production. So my question is, and I understand how that came to be and the politics and the challenges that the system faces, but for you sitting there at NC State with the students coming in today who are interested in going into farming, I know a lot of them are interested in these models that are maybe perhaps not the CAFO model. I know a lot of consumers are interested in that. And so talk to me a little, if you can, about what kind of resources may be going from NC State or toward helping farmers, because these outdoor production systems aren't perfect either. I mean, if you take all these millions of hogs and put them outside, we'd have a lot of problems as well. And I don't want you to talk about that. But if you could just speak to what kinds of resources are being dedicated to help the smaller scale niche producers who really are trying to address holistically the demands that consumers are coming forward with. What kind of technologies might be there for them?
Well, I very much agree that those types of operations, the type that you represent, are not going to be able to meet the demand that is projected. I am very, very glad that there are those niche markets for those types of operations. And to answer your question, I can talk specifically about what we do in our department relative to poultry. We do a lot of workshops for the small flock producers relative to biosecurity, relative to efficiency, relative to nutrition, relative to pathogen control. And I know those types of programs are available certainly within the land-grant institutions. And we feel very strongly that we need to support that in our department especially. And I think you would find that with the other commodity-based departments as well.
If I can just add one thing really briefly, I would not necessarily assume that the systems that we talked about cannot scale down to smaller operations. There's definitely some economies of scale when you're doing things on a large scale, but some of these processes are scalable. So they could benefit small farmers as well.
Yeah, Mark makes an excellent point. I mean, if you look at what has occurred in China, in the households, there are millions of small anaerobic ambient digesters in China. You could do the same thing with the small livestock operation.